Hi, my name is Joe Peterson. I'm a postdoc with Mike Cates at the University of Cambridge, and I'm giving a talk on population balances for full chain constitutive models of living polymers. So what are living polymers? Living polymers are systems of polymers where the polymerization reactions are reversible and therefore non-terminating and said to be alive at all times. These living polymers are often formed of self-assembled type structures where the forces or energies holding the chains together are on the order of, say, 10 kT. Wormlike micelles are a particularly industrially relevant platform for living polymers because when you want to deliver surfactants in a given application, whether it's shampoo or enhanced oil recovery, wormlike micelles give you a great opportunity to tune the rheological properties of the fluid to add value. Nobody wants a runny shampoo, for example. So what is the rheology of living polymers like, and how is it different from the rheology of covalently bonded polymers, for example? We'll discuss this in terms of the linear rheology and the nonlinear rheology. So in the linear rheology, for example, if you plot the storage modulus and loss modulus parametrically, you get this semicircular shape for certain formulation spaces that's indicative of a material with a single relaxation time, which is surprising because worm-like micelles have a spectrum of lengths. You'd think they would have a spectrum of relaxation times, but these formulations evidently don't. In the nonlinear rheology, you can also get shear banding instabilities. So we'll talk a bit about both of these here, but first let's look at the linear rheology. So the theory for linear rheology of worm-like micelles goes back to work by Mike Cates in the late 80s. And the idea there was that all you had to do was combine the existing Reptation model with a reversible scission reaction picture, and you would exactly reproduce this single relaxation time phenomena if you were in the so-called fast breaking limit. The idea is that the chains break apart faster than they're able to natively relax their stress, and in that limit you recover a single relaxation time and a scaling of that relaxation time that goes as zeta to the 1/2. Okay. Now, there have been follow-up work in this area that extended it from not just being reptation, but also adding contour length fluctuations and double reptation, but it's always been constrained to linear rheology. There have been some nonlinear rheology models for worm-like micelles, but they never take into account the same level of detail for the stress relaxation coupled to polymerization reactions. It's always at a more abstract level, right? Where it's been, the models have been developed largely by intuition and not in a systematic way from a reliable microscopic picture. Okay. So in today's talk, we'd like to change that. We would like to take the level of microscopic detail in the original Cates theory and scale that up to, for example, nonlinear rheology models. This talk is mostly going to focus on linear rheology just as a means of developing the framework, but once you've developed the framework, it's more or less trivial to extend it to nonlinear rheology models. Okay, so the first thing that we need to look to is population balance equations for the number density of chains within a given length interval. So the idea is that you bin up the molecular weight distribution into different length intervals, and you look at the different reaction pathways that are available to the polymers, and you describe how material is moved from one bin to another via these different reaction pathways. Right? And here we're mostly going to look at reversible scission. But the material itself, the mass, is not the only interesting thing that's moved around to different bins during these reactions. You also have a distribution of surviving tube segments, for example, that gets moved around. So the idea is that if you have chains 1 and 2 combining together to make chain 3, or the reverse process, chain 3 breaking apart to make chains 1 and 2, if you know the tube survival profile, right, the distribution of surviving tube segments, unrelaxed tube segments in the reactant chain, you can figure out the distribution of surviving tube segments in the product chains. So you can figure out how reactions move unrelaxed tube segments through the molecular weight distribution into different contour positions and so on. And you can write this out as an evolution equation if you have the normal diffusion equation that corresponds to the Reptation model for stress relaxation processes. All it ends up being is an added set of population balance terms appended to the end of that, and those terms scale inversely with the breaking time, for example. And you also have initial conditions and boundary conditions to worry about that show that all the chains are unrelaxed at the initial condition and that chain ends are always stress-free. Okay, so the advantages of this over the models that were done in the late 80s and early 90s is that this approach is systematic. There's no intuition needed. It is detailed in that it gives you the full picture of tube survival profiles at all molecular weights, all contour positions, gives you more information than just the bulk rheology, and that ends up being useful. You should see my other talk for more discussion on that. And the framework is extensible. This is not in any way limited to reptation. As we'll show later, we can look at contour length fluctuations, we can look at double reptation, we can look at chain retraction, convective constraint release, whatever you want, if you have a PDE model for stress relaxation in unbreaking polymers. And if you have a rule for how structural information is conserved during the course of a reaction, then you can write out an evolution equation for the living polymer version of the unbreaking system rather easily. Okay, so as a test case for this modeling framework, we're going to look at the fast breaking limit that Mike Cates studied back in the late 80s, and we're going to affirm that our modeling approach is able to capture the right results. So the first thing that we do, if we take the fast breaking limit, tau b is going to be very small. The reaction terms to leading order dominate our evolution equation, which means basically that the surviving tube segments are being shuffled around through the molecular weight distribution to different contour positions without any meaningful amount of stress relaxation taking place. And as a result, the tube survival probability is, to leading order, uniform at all contour positions and all molecular weights. The problem with that is that violates our boundary conditions. The ends need to be stress-free, which brings about a boundary condition. So in order to look at the boundary layer solution, you do this rescaling in the contour variable S, right? With the smaller your value of zeta, the faster breaking the system is, the closer and closer to the chain end you need to resolve the stress relaxation process, right? So we're not going to discuss the solution to that, the detailed solution to that boundary layer, but what we can show is that if you return to the full governing equations for the tube survival equation, and you integrate over the molecular weight distribution, you integrate over all contour positions, the first thing that happens is all of the population balance terms drop out because those are conservative. And the remaining term, you can go in with the results from the boundary layer analysis and show just from that the tube survival probability, the average tube survival probability, decays as a single exponential with a relaxation time that is the geometric mean of the typical reptation time and the typical breaking time. So it recovers the results from the Cates model without any need for intuition. It just relies on tools of asymptotic analysis and boundary layer analysis and so on. So it's pretty powerful. Okay, but more than that, it's trivial to extend the original equations to add new stress relaxation processes. So for example, you can look at contour length fluctuations by adding in a diffusion coefficient whose rate of diffusion is dependent on the contour position. So the closer you are to the chain ends, the faster this diffusion process is able to occur. You can add in double reptation by basically indexing each tube segment not only by its position along its own contour, but also by the contour position of the chain with which it is co-entangled, the size of the chain with which it is co-entangled. And then you have stress relaxation from one, stress relaxation from the other chain, and the reaction processes added in as well. Finally, you could look at stress relaxation, so where lambda is the stretch at a given contour position. You can do the same thing and look at how living polymer reactions change the stretch relaxation processes in a system of polymers. So that's great. But the really big deal is that we can go to nonlinear rheology as well. And in nonlinear rheology, you need to worry more than about just the tube survival probability, right? You need to worry about what's called a tangent correlation tensor. This sort of tangent correlation tensor approach was first introduced by Milner, McLeish, and Lichtman, and was subsequently improved to the so-called GLAM model. The idea is that if you know the tangent correlation tensor, which is represented as this, square piece of information, if you know the tangent correlation tensor for one chain, for a chain, for two chains that are coming together, you can figure out the tangent correlation tensor for the product chain. And then once you've done that, if you're interested in the fast breaking limit, you can do the same kind of asymptotic analysis and boundary layer analysis that we put together for the reptation case, and you come up with a dramatically simplified constitutive model that can be effectively solved with excellent accuracy in as few as 6 modes. And so it's totally suitable for CFD applications. And you haven't lost any of the underlying physics. You still have the full picture for reptation, retraction, convective constraint release, and reactions at the core of the model. And all of the simplification steps have been done not by intuition, but by systematic use of asymptotic methods and boundary layer analysis, and so on. Okay, so to summarize, the idea is that we were able to put together a systematic framework for modeling the rheology of reacting polymers. You start from population balance equations that describe how material is advected through the molecular weight distribution by reactions, and then you start thinking about what else is advected along with the material. In this case, it was the tube survival probability for linear rheology. For nonlinear rheology, it was the full information in the tangent correlation tensor. And in future work, we hope to be able to extend this to branch structures, and we'd also like to look at improvements to the way that constraint release terms, convective constraint release, thermal constraint release, are modeled in things like the GLAM model, because the way it's done currently may have a number of problems. So if you're interested in practical tools outside of the fast breaking limit, this talk took a particular interest in the fast breaking limit, where these asymptotic tools and the boundary layer methods work really nicely. But if you're interested in those other tools, I would encourage you to come and see my other talk as well. Okay, so with that, I'd like to acknowledge my advisors, Mike Cates, Gary Leal, as well as collaborators on this project, Junju Mu, Ian Stott, Daniel Reed, and the funding from Cafe 4DM and Unilever. With that, I'll take questions if there are any.